magical mail, you know, the post mail.
Oh, right, yes.
Yeah,
the
some,
weapons over
yeah.
here.
And I usually throw them out, and it's like, oh,
Yeah.
flu vaccine. All right. No more about flu vaccines. So we're going to completely change direction in the course, because we're going to be discussing basically for a number of lectures Monte Carlo methods. So I'm going to make a connection now. Why do we care about Monte Carlo methods? It doesn't matter if you're going to use some sophisticated methods later on in your research. If you don't know Monte Carlo methods, you'll be stuck, because at the end of the day, if nothing works, Monte Carlo works. So you need to know everything about Monte Carlo, okay? And in an ideal environment, we will need to have at least one full course of the methods. There is none, okay? I mean, I know there are 10 courses that claim that they discuss Monte Carlo methods over half a lecture. So I'm going to discuss over 6 lectures. And I'm going to go a little bit advanced actually at some points. But really, we need the whole topic. I mean, we need a whole course. I have some references, and I follow actually all of them. But really, the authority that has everything on modern Carlo methods is this book by Robert and Casella. There is, the last thing is an online course, which has lots of resources. So some of the slides, basically, I'm extrapolating from Doucet's notes as well. This book is more compact. It's only like 200 pages. It contains sort of lots of ideas on how to use Monte Carlo methods in physics, biology, chemistry, etc. So it's less algorithmic than the first book. Okay, so let me motivate why we need Monte Carlo methods. We already have said a few things, and I think you did one homework problem. So the posterior that you see on the top, right? So we have some data X. This is the parameters of the system. So the posterior, the way that you see it here, it's never in closed form solution. Okay, so maybe in your homeworks you say, oh, the posterior is a Gaussian, is a student T, but in general the posterior is going to be a computer code. Effectively, because the likelihood is very complicated, and the likelihood is your computer code, and then you put some prior, and at the end of the day, you will need to explore this posterior, which means you're going to need to take some samples. So we will need to know how to do this for this type of distributions. In addition, you see in the denominator, there is a big integral. If you really care about this integral, and we already said that this is what comes up on model selection, how do you calculate this integral if the number of parameters in your problem are thousands? Okay, you know, if you have 2 parameters, you know, or 5, you can use some quadrature rules. But if you have thousands of parameters, how do you do this integral? Okay. Now, even if you don't care about the full posterior, you're only interested in point estimates such as the posterior, the mean of the posterior or the variance, you notice here again, these are all integrals. So even if you don't want to be fully Bayesian to calculate the expectation of the posterior, you have to calculate this integral, the variance, you have to calculate this integral. So how do we do these integrations? Even if you're interested to find the map estimate that looks like an optimization problem, how do you actually calculate the map estimate of a distribution that is defined through a computer code? Do you start taking infinite samples and then say, that's the map estimate? It will never work, okay? So in some sense, even optimization problems, it's an area where maybe Monte Carlo methods would be essential in allowing us to address this. Now, maybe we haven't seen this explicitly, or maybe we showed this with these hyperparameters on prior modeling, but a lot of times, if, let's say, your unknown parameters involve parameters that you really care, but also parameters that you don't care. You remember it, like in the regression problem, this can be the W's, and this can be the alphas and betas that we use to define the prior distributions. So somehow you may be interested to get rid of the parameters θ2 if you don't care. So integrals like that, where you do marginalization to come up with the marginal posterior of θ1, it's sort of essential. So integrals all over the place, and keeps going, because if you already computed the posterior using training data X, and now you want to do predictions Y, this is the predicted distribution. We see it once more. So X is the training data. Now you want to know the probability of future data. So that's the integral in the parameter space of the likelihood times the posterior, right? So that's an integral itself. And if you take the expectation of this, so you're going to have Y times this integral and another integral in Y, so double integration. So the predicted distribution is even more complicated to compute, okay? And again, in real problems, you're not going to be able to compute any of this analytically. And that's not a reason to say, oh, what do I do now? You know, I cannot solve this problem. Well, yes, you can. Maybe it's not going to be efficient the way we're going to discuss it in this class, but obviously there is hope. And finally, you know, I remind you this big Bayes rule type of formula where we do simultaneously model selection, and for the model, for each model we include the parameters as well. So this is the parameters theta k of model K, and this is the posterior of K and theta K jointly. So you don't think that this is weird. Basically, this is the likelihood of model K, and this is the prior of model K times the prior of the parameters of model K, right? And on the bottom, you have the normalization constant, which is basically an integral of this that involves summation over all models, and for each model, integration of all the parameters of the model, all right? So actually, this formula incorporates everything we have done up to now, okay? It tells you the posterior of the model and its parameters, given some data, and it's nothing else but application of Bayes' rule. So again, a massive integral here, and then a summation over the models. Okay, so the idea is we want to compute integrals in high dimensions, and Monte Carlo is going to be the method of choice. So what I'm going to do is I'm going to try to go slowly. If it happens to be too slowly, I will jump 20 slides later on. But I want to repeat basically the example with computing an estimate of pi. Okay, so I told you when we first presented it that we will come back to this topic. So let's see it in sort of in a little bit more rigor. So what we have is we have this square of size 2 by 2, and we have this circle of radius 1 that I denote with d. So remember, S will be the square, and the circle here, I denote this with d. Okay, so we're going to, you remember our experiment is going to be, we're going to throw these darts, you know, uniformly inside the square, and somehow we're going to try to come up with some sample estimate of how many of these experiments have draws that they are inside the circle, okay? And we're going to use that to do some estimation of pi, but somehow we're going to try to generalize this, so we need to sort of strengthen the notation a little bit. So notation, we defined, since we're going to be dropping uniformly these things on this square, we're going to define a random variable that has, it's a vector that has components x and y, which are the coordinates where this thing is going to land, okay? So d is a random variable defined on this square, and it's the location where the dart basically is going to fall. So would you agree with me that the probability, because I am doing this experiment uniformly on the square, that the probability that basically d will land in the circle is the area of the circle divided by the area of the square, all right? Because I do it uniformly, okay? All right, So it's the area, so this is the probability of this random variable, is the area of the circle divided by the area of the square. So let's say we do n experiments, so we throw this n times, and we collect n realizations of this. So D1 will be x1, y1, D2, x2, y2, etc. This is my, my data set. Now, a common sense answer would be that the probability of D being in the circle will be how many times in the n experiments my dart was inside the circle divided by n. You agree? Okay. Now, if you start thinking mathematically, you say, I don't accept this. Why common sense prevails here? I mean, why is this? From where is this coming? So we would like to actually demonstrate this in a more rigorous manner, so that way we can generalize from this trivial experiment. So yes, this is common sense, but we would like to see from where it comes. So I'm going to complicate things a little bit, okay? So I'm going to define first an indicator function, and don't read all of these things, right? Look at the symbol and tell me if you understand what this indicator function is. So you remember x and y are, the coordinates for every time, I hit in a given location x and y, uniformly of the square. So what is this indicator function? By definition, it's 1 when x and y is on the circle A, otherwise it's 0. Okay? And by the way, this is a function of the random variables x and y, but itself is a random variable. Okay, so if you see it as a function or as a random variable, it's all the same thing. So let me rewrite. You remember I mentioned that the probability of D being on the circle is the area of the circle divided by the area of the square. So let me rewrite the area of the circle with this integral. So I want you to tell me that you agree with me that this is correct. Is this the area of the circle really? You remember before my previous equation had an integral over a of dx dy. Now I have an integral over the square, but it's an integral of the indicator function. Does that make sense? Why it makes sense? Because this thing inside the integral is 0 if I am not on the circle. Okay? So it's nice writing like this because the domain of integration is the same. All right? So this is the same as before. This integral is 4. Okay? Now I'm going to put the 4 over there, and immediately what do you see in this integral? That to compute the probability of D being in the circle is this integral here. And to make life easy, you know what's 1 over 4?
Square.
Because the square is 2 by 2, so what's 1 over 4? And I'm doing this experiment uniformly. So what is 1 over 4? It's the uniform distribution for x and y over the square. Right? 1 over 2 times 1 over 2. So what is then this integral? So here, again, don't be bothered about this is like a function of x and y, or it's a random variable, times this probability that you told me it's 1 over 4. So what is this integral? It is the expectation of this indicator function under this uniform probability 1 over 4. All right? So basically what you're telling me, all right, what you're telling me, where is it? What you're telling me is, I don't know why I'm writing all of these things. So what you're telling me is basically that this probability is nothing else but the expectation of this random variable. I denote this as V here to simplify the notation, under the uniform distribution defined on the square. All right? And now you may say, well, big deal, okay, you introduce all this notation, why do I care? Well, do we have any way to approximate with samples the expectation? What laws of statistics actually tell something about the sample mean versus an actual expectation? I mean, if I take basically n experiments and I take the sample mean of these indicator functions, will this be an approximation of that? Based on what law? How do we call that law? Or what laws? Because they are all will give you the same answer.
Number, central limit, or large number?
The law of large numbers, or the central limit theorem, or all versions of that. All right. So effectively, now you see, by the way, so I'm going to come back to this, right? But if you approximate this expectation with a sample mean, aren't you going to actually get, what was that nice formula? Aren't you going to get just that? So do you see that from where this is coming? All right, this is basically a manifestation of the law of large numbers and this derivation that I just did here. Okay? But very simple derivation. All right, so I want to remind you very fast the various forms of the large numbers. Again, we have seen this, so this is sort of a review. If you take samples from any distribution that have this mean and this variance, and we assume in this case is that the variance is finite, basically as the number of samples goes to infinity, almost surely the sample mean is equal to the actual mean of the distribution. So that's the strong law. The weak law basically says, well, they're all the same things, but the sample mean as n goes to infinity converges to the true mean of the distribution. And then, or if you want to see it actually in a probability sense, the probability that you will be more than epsilon away from the actual mean goes to 0 as n goes to infinity for every epsilon. Right, so you can set basically any distance and say the probability I will be away, even if this is very small, as n goes to infinity, the probability is equal to 0. Okay, and then, by the way, I'm going to need these derivations later on, right? You can, if you take the expectation of the sample mean, because the xi's are independent, all right, so you're going to get 1 over n and then n times the expectation of each of them, so you get mu. So you remember the sample mean, it's an unbiased estimate of the true mean, right? We had mentioned that before. Similarly for the variance, you get it is the true variance divided by n, all right? The true variance divided by n. So remember those things. And basically using those things, the central limit theorem says that as n goes to infinity, xn follows a Gaussian distribution with the mean, the actual mean, and a variance sigma square over n. And again, what you need to appreciate here, right, if you haven't really thought deeply on these things, is that the actual x's come from any distribution that has a mean mu and a variance sigma squared, but the sample mean always follows a Gaussian distribution. Right? But again, remember, the xi's are from any distribution. So obviously there's something there. Right? You can philosophize about it. How fundamental Gaussian is in this type of things. All right. So let me, now that we did the central limit theorem, let me return back to our little experiment. And so we define an indicator function. This is a very general function, right? So before we had the indicator function that we will hit the circle A, right? So if you compute the expectation of each of these indicator functions, so if xi is an indicator function, notice that either I will hit the circle and the indicator function is 1, or I will not hit the circle, the indicator function is 0. So this is the probability that I will hit the circle, and this is the probability that I will be outside the circle in the square. So the point here I wanted to make is that the probability of hitting the circle is the same as the expectation of these indicator functions. So which means when I computed how many times I hit the circle, really the sample mean converges to the expectation, which is equal to the probability that I hit the circle. Okay, because the two things are the same. Okay? All right. So, so we gave a statistical interpretation of this, okay? And so this is the sample mean of this indicator function. So as n goes to infinity, basically this converges to the expectation of the indicator functions under this uniform distribution of the square, okay? And so effectively, if the probability of hitting, you remember the formula we had for the probability of hitting the circle was the area of the circle divided by the area of the square. The area of the square was 4, right? And the area of the circle was pi 1 square. So really, the probability of hitting the circle is really analytical, it's pi over 4, which means this sample mean, it's actually an unbiased estimate of pi over 4. So effectively, you can envision that, you can write that Sn is pi over 4 plus some error, okay? So what I want to do now is, since we are introducing Monte Carlo methods, to start telling you something about the error. How much error do you do actually using the sample mean to approximate pi over 4, okay? Can we say something about the error? So you remember the variance of the estimator is, you remember the estimator is basically the sum of all the indicator variables over n. So when you take the variance of that, you get 1 over n squared. And then these are IID variables, so you have n times the variance of any of them. So you basically get the variance of the estimator is 1 over n times the actual variance of these indicator functions. The error, if you like, if you take the square of this variance, and I'm writing it analytically here, the variance is the expectation of this square of the square of S minus the mean of S, okay? And you remember this is really our probability that we hit the circle. So this equal to that. There's nothing here, but I want you to think that really the square root here is nothing else but the mean square error, right? This is the actual, basically, probability that you want to estimate. That's pi over 4. This is the estimate, right? And because there is an expectation there, so this is the mean square error. So the mean square error, all right, is the square root of the actual variance divided by square root of n. So basically, what we have shown here is, for at least a simple experiment, that the error, this mean square error, varies as 1 over square root of n. This is the most fundamental, basically, aspect of Monte Carlo methods, that the mean square error varies as 1 over square root of n. I will generalize this, right, and I will show you that this is independent of the dimensions, but for now, this is what the error is. So the mean square error between this sample estimate and the true estimate decreases as 1 over square root of n. Okay, if nothing else, this is what you need to remember at this point. And if you want to, this constant here, the square root of the actual variance, you can actually estimate it exactly. Can you tell me from where this thing came? So this is the true variance. Why does it look like that? Help me. You remember the true probability was pi over 4, right? So what's the variance? Is the expectation of x squared minus e of x squared. So this is the expectation squared, so pi over 4 squared. And why that first term became pi over 4 only? If you look for the expectation of the indicator function or the indicator function squared is the same. It only takes values 1 and 0, okay? So this is really a Bernoulli variable, okay? So this is the variance of a Bernoulli variable. So the expectation of the indicator function squared is basically the same as the expectation of the indicator function, which is pi over 4. So the actual variance is this number, okay? And again, we don't really care about this number. What we care is this 1 over square root of n, but I will use this in the calculations that you will see shortly. So let me, the variance, so we said is this. So what I'm going to do is I'm going to use the central limit theorem. and I'm going to say the sample mean converges to a Gaussian that has mean, the true mean, and a variance which is the true variance divided by n. Okay? All right? So I'm going to do some trivial calculations now playing with Gaussians, okay? And you can, for those who have know how to use probability tables with the CDF of the Gaussians, they will appreciate what this type of calculations are all about. So let me calculate the probability that the sample mean is this amount away from the actual mean. So forget this thing, right? If I give you, you know that this is a Gaussian, and if I tell you, find me the probability that I will be 2 times this away from the mean. Will you be able to do this with Gaussian tables? Yes? So basically I claim here, right, that this integral is 2 times 1 minus phi calculated at 2, all right, where this is the CDF of the normal Gaussian. Can you imagine from where this is coming? What type of distribution is this minus the mean divided by this term, by basically sigma over square root of n? It's a standard normal, right? And I'm asking you now to compute the probability that I would be away from the mean by the amount 2 of the standard normal, so being greater than 2 and less than minus 2, and that comes 2 times 1 minus the CDF computed at 2. Yes? Draw a Gaussian, say this is an absolute value, right? So this has to be means greater than 2 or less than minus 2. The two things are the same. So 2 times 1 minus the CDF computed at 2. Okay, all right. So basically, this is the probability of your sample mean to be away is given by this. Okay, I can actually generalize, and there are in the literature many inequalities that can be extremely practical when you use especially experimental data. So if you want the probability not to be larger than this amount, but larger than any number epsilon, that's an accuracy that it's of interest to you. So it comes out, this is basically, you can generalize this result. This is what the answer is. And you can write this in terms of the complementary error function that is related with the CDF. And if you use sort of some approximation of this for large n, you can see actually that this is e to the minus epsilon squared times n. This is sort of very standard error estimate for these Monte Carlo approximations, okay? A lot of the details here don't really matter, but the fact that you have, so you're interested on this being greater or equal to epsilon, you have epsilon squared times n, okay? So this last result, it's a sort of an upper bound, if you like. This is the exact answer, but you can see the dependence on epsilon more explicitly by that term. So let me be practical now, and I'm going to compute for our estimator what is called the coefficient of variation. You may have seen this actually from slides on the first lecture, so you see it once more. The coefficient of variation for any random variable is basically the standard deviation, which is, this is the exact, I'm using here the exact actually variance, okay? So you remember the variance of the estimator, right, is what? Is the actual variance divided by n. All right, so you have basically, this is the actual variance divided by n, and the mean is pi over 4. Okay? So the coefficient of variation, exactly for our estimation here, is 0.5233 divided by square root of n. So let's see the following. If you want your coefficient of variation to be 10%, the number of samples you need is 28. If you want the coefficient of variation to be half of that, 5%, the number of samples you need is 110. If you want to go down to 1%, you need more than 2,500 samples. Right? Very trivial problem, but somehow you can reverse these error calculations and say, if this coefficient of variation that I can tolerate is 1%, well, you know, this is how many samples you will need to take in your problem. Okay? And you notice this keeps increasing significantly as you reduce this coefficient of variation. But one way or another, okay, I want to emphasize what you need to remember is that the approximation error always varies as 1 over square root of n. Okay, so the approximation error varies as 1 over square root of n. Now, you may say this is not very good error. It would have been nice if this was n or something else. But you notice something very important. Okay, maybe it doesn't solve this example, but there is nothing about the dimensionality of the problem. Okay, and we will see this. I will emphasize in the coming up slides. Okay, so the approximation error is of the order of 1 over square root of n. There is several inequalities in the literature, and some of them are very powerful. You know, when you try to do estimations from experiments using data, and so you know, don't sort of bypass them as simply mathematical useless inequalities. They have lots of interesting significance here. So, for example, you know, you remember I told you before that this n epsilon squared. So there is another this bursting inequality that looks like this, okay, and different approximations, and I mean you can prove here that the probability that you would be away from the mean by this amount is actually less than 0.05. So in some sense, this is very useful because everybody cares about the 0.05. So actually what that epsilon here is, it's actually log of 40 divided by 2n square root. Okay? And you have to trust that actually if you take this and you plug it in there, you will see indeed that you get 0.05. So it's not magic. So actually whatever you need to derive this, it's on the slides, and I think to convince you that these are not coming from nowhere, I gave you actually links on Wikipedia and other places where you can see the derivations. All right, these are sort of trivial MATLAB results. So if you take, you know, so Sn, right? The sample estimate converges to pi over 4. So obviously this will converge to 0, and you can see with a number of samples how obviously with some oscillations you converge to 0. And so effectively by taking 1,000 samples, you have the right answer. If you repeat this many times, this is the type of estimates you will get. Okay, they all sort of converge to 0. If you want to actually, you know, compute the sample variance, you can do that, and also you can then see how the sample variance, it actually matches this plus minus that true variance divided by n that you know we computed. So this is plus minus, if you like, one standard deviation. So I cannot see them clearly here, but these are some dotted lines, I think, and they bound basically the sample variance that you compute, you know, from the samples. Okay. I think I'm going to give you a formula for the sample variance. Actually, let me, you know, you can study this plot. You know, it's I think from maybe the Bayesian core reproduction of one of the figures. So, for example, here what you see is an estimation of using samples of the standard deviation of the estimator. Can you tell me where the 1 over n and 1 n minus 1 are coming? Look at this thing and tell me, you know, where this whole thing came from. I don't want to bother you about the 4r squared here because the calculation that he has in the book is making not an estimate of pi, but an estimate the area of the circle. Okay, so that's why there's a 4 times r squared. No problem, r is equal to 1. But I want you to tell me where is this? Why is this actually our standard deviation, the sample standard deviation? So there is. Where did the 1 over n came first? You remember, so we are, gonna, we have an estimator, right? And we're gonna compute the error bars on that estimator. So we said that the variance of the estimator is what? Is the true variance divided by n. So the first n, so this must be an approximation of the true variance, and then the 1 over n for the estimator. And for the true variance, I put 1n minus 1 to make it unbiased. You remember, for Gaussians, if you, rather than having 1 over n, you put 1 over n minus 1, okay? For big n's, it will not matter, but you put 1 over n minus 1, and this basically is the summation of the indicator functions for each data point minus, the sample mean, if you like, okay, the whole thing squared, okay? So, so if you repeat this experiment, you can actually compute many times. You can compute error bars divided. You can compute the actual error bars from the estimator, where I use the actual variance, right? So this is the theoretical error bars. So this is, I suppose, these lines that you see here. These are plus minus standard deviation where I use the true variance. Then I compare it with these dark areas, which they use the sample variance so that you can see they coincide. And these points are effectively the estimator basically for different number of Monte Carlo samples. So, if you have an experiment, this is maybe something you will need to do. The only thing I believe you will not be able to do is to actually plot the exact, the exact error bars in your problem, because you will actually not know the variance, the actual variance in your problem. Okay, so you will not be able to do this. So this is what you will be able to do, and I think everybody's going to be happy with it. Okay, so you plot this, all right? You say this is my confidence of the predictions. You don't really have this, but now we have it. Okay, so let me try to keep moving. We don't really care about the square and the circle and the pi, so we need sort of to generalize things a little bit. So. Let me stay. I said I don't care about the circle. I noticed this slide still talks about the circle, but actually in n theta dimensions. So imagine that now you have a sphere in 1,000 dimensions. Have you seen a sphere in 1,000 dimensions? I'm actually going to tell you some things that you maybe your imagination is not going there yet. Okay, so we have a sphere that is defined in high dimensions. Okay, so this is dimensionality, and so we have a cube in let's say 1,000 dimensions. We have a circle inside the cube, and these are exactly the indicator functions that we had before. So these are, we are 1 when we hit this hypersphere, all right, in n theta dimensions, and it is 0 otherwise. The bottom line is the rate of convergence of the estimator, right, in the mean square sense is independent of n theta and is equal to 1 over square root of n. So it doesn't really make a difference if you do this in 2 dimensions for a circle or a sphere or a hypersphere. It's actually the mean square error varies with n as 1 over square root of n. So this is sort of a very remarkable result, and when you read papers, everybody says, oh, it's independent of the dimension. Well, that's what they mean, okay? There is nowhere the dimensionality of the problem coming in this mean square error. It does not depend on the dimension, it only depends on the number of samples. Now, this is contrary to all the deterministic methods actually that use sort of quadrature rules or some collocation grid. And usually in all of those problems, and I'm going to show you some schematics to come, the rate of convergence is 1 over n to some constant divided by n theta. So the convergence deteriorates with n theta for all other deterministic methods. Okay? That R there has to do with the smoothness of the contours defining this sphere here. And because you're going to have to discretize it, but the bottom line is the convergence is 1 over n constant divided by the number of dimensions in your problem. All right? So effectively with deterministic methods, and I will show you numbers, to get this convergence rate that you get with Monte Carlo, you're going to have to use more and more and more and more n to match that convergence. Otherwise, for a given n, the convergence here is way worse, right? Because it's 1 over the number of dimensions of the problem. Which means, really, Monte Carlo method is really the only method that's attractive to do this type of calculations when n theta is large. So I know you don't like the circle, and I told you I was done with it, but so since we talk about the hypercircle, this hypersphere, let me give you some very precise results to get an appreciation of what's going on. So the volume of a hypercube in n theta dimensions is given by this wonderful formula. Okay? So, so we have a hypercube, right? And inside it we have a hypersphere of radius r equal to 1. And this is in n theta dimensions, so the volume of the hypercube is given by this nice formula. If you don't believe me, the derivation actually it's like 2 lines. And somewhere I had this in some earlier slides, but you can click here and see the proof. So this is the volume. So we have so the volume of, if we take the hypercube to be from -1 to 1, all right, in n theta dimensions, so the volume of the hypercube is 2 to the power n theta, okay? And if you use n samples and you compute the estimator that we had before, which is the variance of x divided by n, this is, you remember it's a Bernoulli distribution, is the probability that you will hit the hypersphere minus the probability squared, the same formula I had before. And pi squared is way smaller than pi, so this is approximately pi over n. And let me give you what the exact pi is. The exact probability that you will hit the hypersphere is the volume of the hypersphere divided by 2 to the power n theta. And you know what happens, how big this probability is when n theta goes to very high? It's tiny. So the idea here is a hypersphere in high dimensions occupies an extremely small of the volume of the hypercube. Not the way that you envision in 2D and 3D. Okay? So effectively, when you do this experiment and you throw this on a hypercube, right, on this hypercube, it's like trying to hit the hypersphere, but the hypersphere is on the boundaries of this hypercube. There's nothing there. You cannot, basically you have to try the experiments millions of times to hit it once because its probability is very small. Okay? So, you can see actually this if you calculate the coefficient of variation. So you take the exact variance. So this is the standard deviation of the estimator. All right, this is exactly what we did with the circle and the square. And so you put here the approximation of the variance. This is the expectation. So this and that give you square root. So look what happened. As the number of dimensions go to infinity, the coefficient of variation is basically approximately becomes like that. So if you use a number of samples to be 100 times this probability inverse, then the coefficient of variation is 0.1. So if you put this thing in there, right, you get 1 over 100. So you get 1/10, so you get 0.1. But look what happens. If you compute this probability, right, in 20 dimensions, and you see how many samples this is, the number of samples is 10 to the 9th. So basically, in 20 dimensions to get a coefficient of variation that's 0.1, you need 10 to the 9 samples. A lot. Okay? So basically, yes, Monte Carlo methods have nice convergence rate independent of dimensionality, but then you see here also the difficulties on actually operating in high dimensions, that the number of samples to achieve some reasonable coefficient of variation is extremely, extremely high. I mean, imagine if this were runs that require, let's say, running your computer code. There's no way to actually get statistics that are reasonable to run it only, I mean, people run, let's say, 50 times and they say, oh, here's my estimate from my sample estimate. Well, it's not very good enough, because if you do this in 20 dimensions, you better have 1 million or 1 billion. Is this 1 billion or what? Yeah, something like that, okay? All right. And then I give you basically another sort of similar type of state. Okay. All right, so let me keep moving. Literally now we're away from circles and hyperspheres. So we want to calculate the expectation of a function of theta, where theta basically follows the distribution pi of theta. So you can think of this integral, for example, being the pi of theta, let's say, being the posterior distribution, and you want to calculate the posterior mean or the posterior mean of this function f of theta here, okay? We're going to assume some regularity here, that the expectation and the variance basically are finite, so we don't have to worry, but somehow we need to be able to compute this. So when we did the experiment with the circle, this pi of theta was a uniform distribution, right? So now it's an arbitrary distribution. So everything we said before, it is applicable here. So this, you can approximate it basically with the sample mean, okay? This is what it is. And where the samples theta are derived now, are sampled from the distribution pi of theta, okay? And so this is basically a restatement of the result that I had before for the circle. So if you take the sample mean, asymptotically, basically, it gives you a very good approximation. It's equal to the expectation under the true distribution of f of theta. And if you want the variance, exactly the same result, right? The variance of the estimator is the true variance of f of theta divided by n, okay? And if you want to write this, all of this together with the central limit theorem, there's nothing new here, is this sample mean, as n goes to infinity, approaches a Gaussian with this mean and this variance. Okay, exactly the same results as before. Now, obviously, what is new here that you need to start thinking about is now this samples theta come from the distribution pi, and someone will say, well, you remember the posterior is very complicated. How do you sample from something very complicated? And this is what we will spend time to discuss in the next few lectures. Again, the rate of convergence is independent of the dimension of theta, okay? I am trying to emphasize this as much as I can today. All right. I am going to bypass some of the notations, and I'm going to go directly to the third bullet. So imagine that somehow we have learned how to take samples from a distribution. So we have a distribution of posterior pi of theta. We take n samples. You remember somewhere in an earlier lecture, I told you, and I said I'm going to come back to it, we introduced the empirical measure of a distribution that was looking like this. It's a bunch of delta functions centered on each of the samples, and these delta functions are all weighted with 1 over n. Okay, so this is something new, okay, if you haven't thought about this before, right? Usually when you take samples and somebody tells you approximate the distribution, what you do is you say, oh, the distribution is a Gaussian, let me approximate the mean, the variance from the samples. Here actually there is nothing, no parameters. You use directly the samples, right? And from the samples you create an approximation of the distribution that's called the empirical measure of the distribution. So it's a non-parametric way of actually working with the distribution. This is very important. Okay, very important. We don't fit to any distribution. We take the samples and we make an approximation of the distribution that consists of these delta functions. Okay? Again, the notation here, hat, is to indicate that this is the empirical measure of the distribution, and I put a subscript n to indicate that I'm doing this using n samples. Okay? Now, there is, of course, a significant value to this, but let me show you something interesting. Okay? Actually, let me see if I can go directly to the next slide, if it has. Yeah, so let me go to this slide. Okay, I'm bypassing, you know, all the intermediate steps because obviously you can follow everything I say. So let me calculate the expectation of this function f of theta. We need to compute this expectation with respect to the true distribution p, but what I'm going to do is I am going to use, instead of p, I am going to use the empirical measure of p. So we have taken some samples from this distribution, right? So we cannot really calculate this exactly. So I'm going to say, well, let me see what is the physical meaning of this empirical distribution. So let me compute this expectation of f under this empirical distribution. So what I have done here is I put this big summation there, all right, is the empirical distribution. The rest is the expectation. We can see this is the expectation of f of theta, and here is the probability, and I use the empirical distribution. So I can put the summation outside, and then I have 1 over n, f of theta. I have these delta functions. Now you remember from calculus, when you integrate a function, you have this delta function centered at the point theta I. What you actually get is f at theta I, because delta function is everywhere 0, and it has infinite support basically to that point, and when you integrate it, you get 1. Makes sense? I mean, that's the whole idea, right? If you take the integral of delta function, you get 1, but the only contribution you get in the integral is around that location. So in this case, we don't have the integral of delta. We have an integral of this function where the term here is f of theta. So everything will drop out because the delta function is 0 everywhere else, but the only contribution that is going to come up will be f of theta I. So the integral, basically, if you take the integral of f of theta times this delta function set at theta I, you get f of theta I. This is an amazing result now, that if somehow we compute an approximation of the expectation of f using not the true distribution, but the empirical measure of the distribution, actually the estimate we get is our sample mean. Okay? So now maybe you start getting an appreciation of this. So effectively, this empirical measure is really the Monte Carlo estimate of the distribution, because if you use it, then you get all the Monte Carlo estimates we discussed up to now. Okay? So if you use this empirical measure to get the mean or the variance, you will get exactly the sample mean or the sample variance that we have seen up to now. Okay? So effectively, the calculation is substitute the true distribution with the empirical measure, and then you're in business. Okay? So for example, if you want to calculate again the variance, right? Rather than using the true variance, you're going to use the sample. Rather than using the true distribution, you will use the empirical measure, and this expectation will give you this, and then that thing will give you that, which is exactly what we calculated. Okay? So let me go back now to be sure that we did not miss anything on the previous slides. Okay? So I wanted to show you how, so if you get samples, if you get this empirical measure of a distribution, what do you plot? So when you write a research paper, this is what you plot. All of these weights, right, are the same, 1 over n for these delta functions. So these samples that you see here, this is your empirical distribution. And you notice there are more of the samples, right, around the peak of the distribution. So obviously, if you try actually to calculate the CDF of the distribution, or if you try to calculate, the mode of the distribution using samples, you will actually come very close to the right answers. Okay? But the bottom line is, what is new here is that somehow we have all these delta functions, right? And this is an approximation, a non-parametric approximation of any distribution, and I show it here for a Gaussian case. Now, so this picture, if you want to get a sense on so we calculate expectations, right? These are integrals. If you want to see the differences between what you do in a deterministic integration of a function that looks like this, okay? You basically put a uniform grid of points, okay? And you use a quadrature rule, and you approximate things like that. But actually, when actually, let's make this to be our distribution, okay? So this is our distribution, okay? So if you try to, for this distribution to do it with Monte Carlo, you notice the only points you will use is where the mass of the Monte Carlo is located. All right, so this will be our delta functions where we will do the calculations. You're not going to go and put points where there's nothing there. So when you take samples from these distributions, these samples are going to be more and more where the peak of the distribution, where the mass of the distribution is. But the deterministic methods, the samples are everywhere uniformly, more or less, because in the deterministic methods, these integration schemes don't pay attention to what function you integrate. They say, oh, I have this wonderful rule, give me a function. Well, this wonderful rule doesn't really care that the function is 0 there and nothing is going on there. The Monte Carlo method does. Okay, so this is very important. All right, so this is, if I have two arguments, okay, I'm writing explicitly for two variables. So the empirical measure looks like this. I just wrote it explicitly as delta functions on center around θ1 and θ2i, okay? I against the sample, θ1, θ2 are the two variables. And let me give you a wonderful result, right? A trivial result. If you really want to marginalize this and want to get rid of this, basically you have these delta functions only on exactly the same θ1s that you use up there. Okay, because when you integrate it, the θ2, the delta function is part of delta 2 will actually give you 1, and those same samples, you can actually reuse them to compute the marginal distribution. And I mentioned before, if you want, let's say, the mode of the distribution, if you have an approximation of a distribution with its empirical measure, effectively to find the mode of the distribution is like asking what is the sample θi that actually maximizes the distribution, okay? So this problem also can be posed very easily with the empirical measure. Actually, I already have told you this. We don't need to do this, okay? This is a repeat, okay? So this is basically, you can look at the nodes. Basically, there's a lot of different trivial results. So for example is, let me ask you the following thing. Don't read what it says here. If I give you an integral of f of x dx, and I tell you to compute it, and compute also the error with Monte Carlo, what will you do? So I give you a function, and I say, find me the integral of f of x dx. Again, don't read. There's no probability or anything. I just tell you have an integral of f of x dx. How do you bring Monte Carlo methods? We said how we approximate the mean, but I don't see any probabilities or anything like that. So what do you do? Huh? If there's no probability, you bring the probability in. How do you bring it? You multiply there by 1, and you make 1 the probability of what distribution? Of the uniform distribution, right? So you take n samples from the uniform distribution, and an approximation of this will be basically n 1 over n times that integral. Okay? So I'm doing this for various examples, approximating basically the integral of f of x dx from 0 to 1 or something like that, x squared cosine of pi of x, and again, you can get the error bars, you can do anything you want to with this type of approaches. Okay, so here is I'm computing the variance actually, so I'm computing the error bars in this estimator, and the lines that you see are the exact variance, and this is how the sample variance basically converges to the exact value. Okay, and I am not going to repeat what I did for the circle, right? But if you are asking, let's pose the problem as follows, right? So you want to compute an integral, okay? And this is the true value of that integral, okay? This is the sample approximated integral, okay? And you want this integral to be less or equal, you want the probability that you will be away from the true value by epsilon to be 1 minus alpha. That's what everybody does in statistics, right? I want to know how many samples do I need to make this probability equal to 1 minus alpha. So you can actually show, all right, that the problem is a little bit complicated. The algebra is exactly as in the circle problem. You can show that the sample variance, right, has to be less or equal to n times epsilon squared divided by this inverse CDF function computed at 1 minus alpha over 2. I know you are not going to believe me, and you will not believe me unless you actually look on the circle problem, all right? This is using just tables. You know how to compute this, right, from tables of the normal standard distribution, right? So it comes up that the number of samples has to be greater than the sample variance, because you don't really know the variance, the true variance, times this inverse CDF divided by epsilon squared. So this will give you this probability. And the other point I want to make here is that this sample variance depends on the number of samples. So we're asking, what is the number of samples to drop this, so for this probability to be 1 minus alpha, and then it comes out that the number of samples has to be greater than this times that, divide by that times this, and this sample variance involves n on it. So you have to do this iteratively. Okay? So, and again, it will converge basically in little 2 steps here. So, and again, I give you a whole algorithm, right? So, let's say you do n1 tests, you check if this is satisfied. If it is yes, then you stop. You say I only need n1 samples. If not, you form basically the difference and you see how many extra samples you may need. Then you repeat this for k extra samples. You check if this is satisfied. If not, you iterate. Okay? So just remember that the true variance is never known in your actual experiment. So you need to approximate this with sample variance. So these inequalities that I was showing you before, that they use tables of normal random variables, they couple basically the n explicitly from this term and also from the estimation of the variance. And by the way, you can change this and put any criterion you want to. If you want to calculate the probability your estimator to do anything, to be between this value and that value, you can actually use normal tables, because the estimator follows the central limit theorem, that's a Gaussian, so you can manipulate it in any way you want it. Okay? Let me see. So this is a very nice example, actually, that involves a little bit of algebra, and it is from the Bayesian core book that I gave you one chapter some time ago. So let me put all of these things up, and I'm going to tell you on how you can use Monte Carlo estimation to calculate Bayes factors, right? Because can somebody remind me what's the Bayes factor? I forgot. Because it's like my landing yesterday with all the wind, somehow my head is spinning. So what's the Bayes factor? Is the ratio of what? These big integrals, what were the big integrals? Big integrals. It's the ratio of two big integrals for two models, right? Here, let's say model 1 and model 0. But what were those big integrals of what? You remember Bayes factor, model selection? What term in the Bayes rule comes in model selection? Exactly. It was basically the marginal likelihood. Okay. So basically, is the likelihood times the priors with all the parameters integrated out. Okay. And the ratio of those two for the two models is basically what defines the Bayes factor. So I'm going to explain this example, and so you can get a sense that this really can be useful if you want to compare two models, right? So there is a particular data set, and we collect two different some samples. So maybe you sample one day x1 to xn, and another sample is y1 to yn, okay? And so we assume that the two samples came from two different distributions, because we don't really know the true distribution, right? So the sample says it comes from a Gaussian with some mean mu x and a variance sigma squared, and another sample comes from another Gaussian with the same noise but a different mean. Okay? And basically what we want to test is the hypothesis that the means implied by both samples basically are the same. So the zero hypothesis is that we want to test this, that the means mu x and mu y are the same. Okay? So again, we have the samples. They come from this distribution. Y comes from this distribution. And we want to check actually if mu x is equal to mu y. So in this problem, because there is noise, we're going to assume some prior in the noise. So we're going to take a Jefferson informative prior, and the Bayes factor 1, 0 is basically the marginal likelihood. The likelihood here, by the way, don't get confused. This is the correct way of writing it. You remember the likelihood is a function of the parameters given the data, even though lots of times we write this P of D given the parameters. This is the right way to write it, times the priors. And I'm taking the priors on mu and sigma squared to be independent. And remember model 1, all right? If model 0 says mu x equal to mu y, model 1 will have mu x different from mu y. So I'm going to have a prior on mu x and mu y times the prior sigma squared, and then integration of sigma squared out, and integration of mu x and mu y out. And model 0, because mu x and mu y are the same, you have a prior only on mu, the prior on sigma squared, which is the same, and integration sigma squared and mu. So what I would like to show you is how on this setup, you can actually calculate this with Monte Carlo, doing a little bit of tricks, okay? So obviously, there are lots of integrals here, right? There's an integration sigma squared, integration of mu x and mu y, okay? So what we're going to do is we're going to do a little trick. So in one model, the parameters are the same, right? The other model, the parameters are different, but we would like somehow to use the same prior for all mu's. So here's the trick. I am going to do what's called reparametrization. And I know it's too early to throw your ideas here. This is a very common way to handle this type of things. So the reparametrization here is, I'm going to write mu x on model 1 as mu minus xi another random variable, and I'm going to write this as mu y as mu plus xi, and this will allow me to put the same prior on this mu as I would put on the model H0. Can you see this? By doing this trick, right, it will allow me to put the same prior on this mu as I would put on the mu on model H0. So for model H1, the priors basically will be written as this prior on mu, which is what I will use on model H0 plus the prior on xi, okay? And I am going to take now xi to be a standard normal, okay? And the prior I'm going to use for mu is going to be a uniform prior. So it's basically an improper, uninformed prior. So the Begues factors basically are written, all this wonderful expression that we see in the bottom. And do you remember this expression here? You know, can somebody make me happy and tell me what is Sx squared, for example, coming in these terms? Because I wrote a few times the likelihood for the Gaussian distribution. And remember, Sx squared is the sum of the square errors, but from where? Of the data from what location? From the MLE estimate. Okay? So, I'm just, you know, again, what you see here is nothing else, right? This terms here or this term is basically the likelihood for the Gaussian, all right? This is mu minus the actual mu of the distributions, which is, I'm sorry, I should have written this differently. Okay, so if I combine those two terms together, right, what do you get in the Gaussian exponent? You get xi minus mu squared, okay? Now you notice here what I have is, I have x bar minus the actual mean, and Sx involves the square error of xi minus the sample mean. So basically I rearrange the square exponential, right, to write it in terms of this Sx terms, okay, and this is very typical for Gaussians. It doesn't matter, okay? You do it your way, okay? You plug in basically this means in the two terms, and this is what you get. So before you do Monte Carlo, you can do some magic first, all right? So the first thing you can do is integrate sigma squared out, okay? So you can integrate sigma squared out actually exactly, and this is what you get, all right? So if you integrate sigma squared out, and then if you look at this integral, can you potentially guess if you actually put this integral on a symbolic calculator, what type you will get out of that integral? Does this remind you of any distribution? Something, you know, you're looking now on mu, right? It's mu squared, there's some constant there, to the power minus n. What does this remind you, the normalization of something? From all the distributions we have seen, you know, okay? So, because we only have 2 minutes, okay, you can actually show that you get the normalization of the student t distribution, okay? So, so if you do this integration in mu, okay, exactly, this is what you are left with, okay? You are left basically with this wonderful final result, okay? So this variable s squared involves known things. Somewhere, no, s squared I defined it before, right? S squared is this, okay? And I also defined this sigma squared like that, and just to make the algebra easy. And basically the Begues factor, and I have here the Begues factor, hopefully this is correct. I have the Begues factor 0, 1, okay? 1 over the Begues factor 1, 0 is this exact term divided by this integral. So the only thing you need to do Monte Carlo is the integral on the bottom. And it's very easy now to see exactly what samples you're going to get, because this distribution in C is a normal Gaussian. So basically what you need is take n samples from the normal Gaussian and then compute the sample mean of that. And this divided by the sample mean will give you the biggest factor. And actually, there is the answer, okay? So this is the answer of the biggest factor. It counts the estimator to be, let's say, 43. But also, you know what you can do? If you take n different samples, you can compute another number. And then take n more samples, you compute another number. And then if you plot the histogram, you can actually get the error bars and every statistic you want on the biggest factor itself. So actually, you know, if you're going to do a model estimation, right, or a hypothesis testing, you need to do this. And you basically, you can see now all the variability of your estimator. And if you want, you can actually compare it with the sample variance, which is, you remember, the true variance divided by n. The true variance obviously has to be approximated with the sample variance. So you can actually compare this with what you see here, and you'll see that the two things coincide. Okay? All right. So what I'm going to do is I am going to stop here, which is a good point because we're going to start tomorrow to tell you a few basic things on random variable generation, and then next Tuesday we will proceed with important samplings and more important things. Okay? Because there is a homework due, and I don't know how much help you got from the TAs. If anybody wants to see me, you email me today or tomorrow or on Monday, and we will arrange basically for any time so we can discuss the homework. Okay? So just let me know.